Hi, welcome to video 7.1a, Introduction to the Area Between Two Curves. So chapter 7, we're only doing two sections. These are applications of integrals. One is area, the other one is volumes. We'll be doing volumes by taking regions that we've been finding the areas of and revolving them or rotating them on a horizontal or vertical line, giving us a solid. And also we'll be doing volumes by cross sections. I'll come back to that later. Okay, so area between two curves. So far, we've seen the region bounded by one curve, the x-axis, x equals a and x equals b. Now, if that function is above the x-axis the entire time between a and b, such as this graph right here, then the area is the integral from the left border to the right border, x equals a to x equals b, of f of x dx. Remember, these are the heights of the rectangles, and these are the common widths of the rectangles. If, on the other hand, the function f of x is below the x-axis the whole time between a and b, then the area, the problem is that the integral will end up being negative, because if you move from a to b, your dx's are positive, but your f of x's are all negative. So you're going to have width times height, which will end up being a positive times a negative, and you're going to add up all these negatives. So the integral itself will be negative. Area, of course, has to be positive. So there's three ways of doing that. You can take the absolute value of the integral. You can stick a negative in front of the integral, excuse me, or you could reverse the order of the limits of integration, which is the same as sticking a negative in front of it. The most popular one is this one, and they actually will say without using absolute values. I don't know what their problem is, okay? But keep in mind the integral here is negative, but the area has to be positive, so you have to take care of that some way. Now, if it turns out that f of x is sometimes above and sometimes below, i.e. sometimes positive and sometimes negative between a and b, such as this graph right here, what happens here, if you think of area, okay, which is positive, let's pretend this area of that is 4, this area is 5, this area is 9. Well, 4 plus 5 plus 9 should give a total area of 18. However, the problem is that the integral from c to d will be negative. So you can't go 4 minus 5 plus 9 and expect to get 18. So the area is not equal to the integral from a to b, and this is the surprising part, it's not equal to the absolute value of the integral from a to b. What it actually equals is the following, which is the integral from a to c, which is already positive, and then you subtract the integral from c to d, because the integral from c to d will be negative 5, and you want to add 5. And then plus the integral from d to e. Oh, I'm sorry, I forgot this little piece over here. And then minus, because that little piece is below the x-axis, from e to b. So basically, it's very simple. You simply put a positive sign in front of each region that's above the x-axis, and you put a negative sign in front of each region that's below the x-axis. Now, of course, that requires you to find the spots where it changes from above to below, which are the x-intercepts. So the first thing you'll have to do is determine where all the x-intercepts are between A and B. Okay, so obviously here, if I do add them, sorry, it's not 19, it's not 18, it's 22, because I forgot the last piece, okay? All right, now here's what I wanted to explain to you. If you put an absolute value around the whole thing, then you're saying integral from a to, remember we can break up a to b into a to c plus c to d plus d to e plus e to f, but you'll end up having 4 plus negative 5 plus 9 plus negative 4, and that's going to give 4, which is not the area. So forget about putting absolute values around the whole thing when it's partly above, partly below. Okay, so now let's talk about the area between two curves. So now we have the region bounded by y equals f of x. Let me actually change this to, I didn't mean to do that. Let me actually change this to blue so that we can be all color coordinated here, as you know I like to be. So the blue graph is y equals, I'm doing this with my mouse, so give me a break here, of x, okay? All right, so we want the area between the red curve and the blue curve, which would be this green region. Well, just visually, I would think it would make sense to you that if I was to cut out the area bounded by the blue curve in the x-axis and these two vertical lines, which is the blue region, and I was to take my scissors and cut away the red region, wouldn't I be left with the green region? In other words, very simply, the area of the region bounded by those curves. In other words, the green region will be the blue region minus the red region, which will be the integral from a to b of g of x dx minus the integral from a to b of f of x dx. Since they're both from a to b, I can stick them together, and basically what it comes down to is this right here, which is you're going to take the top curve minus the bottom curve. Now, you might think that's only going to work if they're both above the x-axis. As it turns out, it works in any case. Let's take a situation again here where, and let me do these color-coded. Okay, so f of x is the black curve. So y equals f of x is the black curve, and g of x, I shouldn't have done this way, but whatever. And g of x is the green curve. Okay. All right, so what happens now is if you look at the graph, we're looking for the area bounded by this black curve and this green curve, which would be the green. Okay. Now, let's try our top minus bottom and see how that works. If we do top minus bottom, it's actually going to work because the top curve, the one that's above the other, is f of x is on top, g of x is on the bottom. So that's going to be the integral from a to b of f of x minus the integral from a to b of g of x. Well, what happens is if you pretend that this black area is 3 and that this big blue area is 10, obviously, you should expect that the green area will be 7, right? 10 minus 3, which is positive 7. Well, the integral from a to b is negative 3. If that area is 3, then the integral is negative 3. And the blue area is 10, so the integral from a to b of g of x is also negative. And lo and behold, negative 3 minus negative 10 is the required positive area of 7. It'll also work if one of them is above the x-axis and the other one is below the x-axis. So let's say the blue area is 8 and the red area is 3. Well, if I want the area of the region bounded by the blue and the red curves, obviously it's this green area again. Well, the green area should be 8 plus 3, which is 11. Again, if I do top minus bottom, I'll have 8 minus, and of course, the integral from a to b of g of x dx, g of x being below the x-axis the whole time, that red area is 3, but the integral will be negative 3. So you end up with 8 minus negative 3, which is 8 plus 3, which is the required 11. Now, so far, every graph we've seen, both curves, the left and right borders have been these vertical lines, x equals a and x equals b. But that might not be the case. What you might have is simply the two curves intersecting one another. Now, you'll have to first find those points of intersection. And basically, it comes down to the same thing, top minus bottom. Now, to find the points of intersection, of course, you're going to be given y equals f of x, y equals g of x. You're going to solve the system of equations, which is a piece of cake, and it will indeed become the integral from a to b of f of x minus g of x. I know you might be worried that, but part of it's above and don't even worry. It's top minus bottom. It takes care of